And so today I want to talk more about these extremes in precipitation, kind of on the daily time scale. So thinking about like when it rains really hard in a given day, and then like how many days you have to wait in between rain events at a given location. And so getting at this idea of increasing floods and droughts, and not just thinking about it like, oh, well, floods will increase in some locations and droughts will increase in other locations and depends on the season or things like that, but thinking about in the same location, can floods and droughts increase at the same time? And so let's think about the probability distributions again. So this is the same slide that I've shown the last 3 times for temperature. And I just like to show the temperature one because I think that's a little bit more intuitive than the precipitation one. I show the temperature one first. So this, again, just to remind you, this is, in temperature, these are warm temperatures, these are cold temperatures, these are like bell curve, Gaussian curve, probability distributions, or histograms, just telling us, what is the likelihood of various temperatures. So you have some probability distribution, some likelihood of given temperatures in an original climate, and then in a warmed climate, more or less, we're seeing that entire thing shift to the warmer temperatures. So you get a warmer mean, and you get less cold extremes, and you get more hot extremes. Okay, so that's the temperature one. So let's think about what this looks like for precipitation. So here's the same kind of axes where instead of temperature here, now I have precipitation. So this would be heavy precipitation over here and light precipitation over here. And actually, so right here would be like days with no precipitation. And so we're thinking of this like the probability or the frequency, or you could just say the days per year with a given amount of precipitation or rainfall. So just kind of picture what you think that might look like. So if it was like temperature, it'd be something like this. But what's wrong with that? What would that say in particular about like days with no precipitation? Yeah, so Professor Ampini says it would mean it's raining almost every day. And so this would be a pretty odd climate. And this would be very atypical because this is saying that you have almost no days where there's no precipitation, and you have whatever this amount of precipitation is, like most of the days are like that, and then this makes more sense that the really heavy days you have less and less of those. So this is not very typical. And so they usually don't look like this. They usually look something like this, these distributions, where you have lots of days with no precipitation. And then sometimes there'll be like this secondary peak over here. But let's just ignore that for now. And just assume that our kind of base state is like this. You have most of the time, what's most likely is you get no rain. And then it's a little bit less likely to get some rain. And then it gets less and less and less likely to get really high values of rain for that day. Okay, so we could have a situation where as it gets warmer, it could just be rainier. And so that would look something like this, where you have less days with no precipitation in your warmed climate. So you're going down over here, and you have more days with all of these heavier values of precipitation. And so then there's some, point of crossover where it's the same. So that would be a rainier climate, less days without precipitation, more days with more extreme values. You could have a kind of a less rainy climate as it gets warmer, where you have more days with no precipitation, and then you have another crossover point, and down here you have less days with these heavy values of precipitation. And then you could also have kind of just a more extreme climate where you get both. You get more days with no precipitation. This goes up. And then you have kind of a crossover point where these are like your moderate values of precipitation in this range. And these are going down. You have less of these. But then you have more of these extreme values of precipitation in your warmer climate. So these are kind of our three options. And so for this, what do you think is most likely in a warmed climate? So it actually is C with a bunch of caveats, but in general, over a lot of land locations, we actually do expect we expect the answer to be C. And so I'm gonna spend some time trying to explain how this works. And yeah, so it would be at a given location, at the same location, you would get more days with no precipitation and more days with extreme precipitation. And then you're gonna have to kind of have less days with moderate precipitation. Okay, so let's look at the theory as to why this should happen. Okay, so going back to our diagram, I want to revisit this part, that as it gets warmer, the atmospheric reservoir, so reservoir just means like the capacity, so how much moisture the atmosphere can hold. The atmospheric reservoir of moisture increases at 6% per degree Celsius of warming. And this is a graph of that. And so this 6% actually is like a compounding 6%. So that means that like each degree, it's 6% from the previous degree. It's not 6% from some constant baseline. And so that means that you have a graph that curves like this. We call this what? Exponential relationship, that as it gets warmer, this would be like how much water can be in the atmosphere, and this is temperature. So as it gets warmer, more and more water can be held in the atmosphere, and that rate of increase increases as you get warmer. So each additional degree of warming over here causes there to be 6% from the previous degree of warming increase. So we have this exponential relationship where more water can be held in the atmosphere the warmer it gets. So there's our 6%. And then precipitation, again, increases at 3%. Okay, so I'm going to spend a decent amount of time on this, but so first I'm just going to write, I'm going to write this down kind of in note form, and this will probably be the hardest way to explain this, and then I'll come back to a couple conceptual models, and hopefully these notes will make sense after you see those conceptual models. But first I'll just have this written down for you. So our atmospheric capacity, how much the atmosphere can hold in terms of moisture, is increasing at 6% per degree Celsius of warming. Now, our long-term increase in precipitation, this, is increasing less than that. It's increasing at 3% per degree Celsius of warming. So we have another kind of mismatch here. And so that's why I have another exclamation mark, is that these are not matched up. And so that means you're gonna change something else in terms of how precipitation is distributed. Okay, so what happens when we have an intense rainstorm is the atmosphere essentially takes all of the moisture that's available and rains it out simultaneously. So it's going to increase its rain. If it's an intense rainstorm, it's going to increase its rain rate by how much moisture is available in the atmosphere. So since the available moisture is increasing at 6% per degree Celsius of warming, the most intense rainstorms will increase their precipitation rates at this level, at this 6% per degree Celsius of warming. So we expect the amount of rain in the heaviest rainstorms to increase at 6% per degree Celsius of warming. But in the long term, at any given location, you can't be increasing rain by 6% per degree Celsius of warming, because you're restricted to only be increasing your precipitation by 3% per degree Celsius of warming, because that's how much evaporation is increasing. And so you can't rain out more water than is actually available. So in order for the precipitation rate in the biggest storms to increase by 6% per degree Celsius of warming, according to how much is available to rain out, in order for that to be true, and at the same time for it to be true that the long-term average precipitation rate is only increasing by 3%, something else has to change. And what has to change is that there has to be longer intervals between storms. You have to wait longer in between every single rainstorm in order to kind of even these things out, to make these things both be true. So a given location can experience more heavy downpours and longer time intervals between these heavy downpours. And it's not just a coincidence, it kind of like has to be true based on these two initial premises. And so that's where some of the shorthand comes in, where people say more floods and droughts at the same location, or wet gets wetter, dry gets drier is the other phrase. And we talked about last time, wet gets wetter, dry gets drier can have two meanings. Last time we talked about it in terms of location, where wet locations in the current climate tend to get more precipitation in a warmer climate. So those wet locations get wetter. And then the dry locations, the locations that have less precipitation in the current climate, tend to get even less in a warmer climate. So that's one way of saying wet gets wetter, dry gets drier. This is the other way. This is, instead of saying wet gets wetter and dry gets drier in geography, we're saying wet gets wetter, dry gets drier in time, where the wet days get wetter. So the wet days have more precipitation. And then the dry gets drier because you have a longer time period between precipitation events. But I came up with kind of a model for this that I think is easier to understand. And it's using this simple tip bucket model of the atmosphere. And so in this simple conceptual model, we have this thing. This is a tip bucket that actually comes from a rain gauge. So first I'll actually show you a video. Here is someone, and I think they're just trying to show off that they 3D printed this. But the idea is this is what's in rain gauges. This is how we measure rainfall. And so you have water coming in at the top. This is a funnel. So this person is just spraying with a spray bottle into the funnel. And then you have this tip bucket down here that's going to measure how much rain there is. And so these tend to be like 1 millimeter each tip. And so every time that tips over, then it's going to, trips some wire and it records that. The idea here is that you have some reservoir that fills up and then it reaches a threshold and it tips and it releases all of that water. Applying this model to the atmosphere, the evaporation actually corresponds to the water going in. So that's one kind of confusing thing, that in the rain gauge, it's measuring rain, but so forget about that. It's evaporation is the water going in. Then you have the atmospheric capacity, how much water the atmosphere can hold. That is the size of the bucket. So once that fills up, once your atmosphere fills up with water from evaporation, it tips and you get rain. So this is like pretty intuitive actually when we think about rain, because rain comes in clumps, right? It comes in abrupt, events where if you can think about it, if you're out in the ocean, it's just constantly evaporating water. There's just kind of this relatively constant flow of water going into the atmosphere, but it doesn't come out constantly. We don't constantly have like some rain. It comes in these events. And so that's why this simple model works. It's like the atmosphere is kind of constantly filling up, and then some threshold will be reached where a thunderstorm or a group of thunderstorms is initiated, and there's kind of these positive feedbacks, and then all the rain comes out at once. Okay, so let's think about these in terms of like graphs. So just take like 30 seconds to a minute and think about what each one of these graphs would look like in time. That if we start putting this system into motion and we have a constant evaporation. So in that video, the guy was like squirting like some water into there. And so that was kind of not constant evaporation, but let's just pretend the evaporation part is constant, like you have a faucet that's just on. So that we have this constant inflow. So what does this graph look like just in the basic climate? We're not talking about warming yet. We're just talking about in the current climate. What does evaporation look like? What is the amount of water in the atmosphere or the water in the bucket look like over time? And then what does rain look like? Like how much comes out? So what do you think the rain one looks like? A, B, or C? Okay, what do you think water in the atmosphere is? New poll. What do you think evaporation into the atmosphere looks like? Okay, so in this case, we're getting majority correct, which happens to be C. So the evaporation into the atmosphere. So I said it's just constant. You just have this constant value flowing into the funnel. So it's just going to be a straight line, a straight positive line. And so given that, now what do you think about A and B and which ones those would apply to? So rain is like B. Bring back the model and then show you the graphs. So same order: rain, water and atmosphere, evaporation. So we have evaporation is just constant. It's a flow. It's constant and positive, meaning that it's just, defined it as positive going into the bucket. So you have 2 units of evaporation every single time period flowing in constantly. And then the rain and the water in the atmosphere. So this, since you have this constant flow in, the water in the bucket is just constantly increasing, right? Over time, it's larger and larger and larger and larger over time until it fills up to some point and it tips and it goes down to 0. It resets itself down to 0 in the bucket. So it tips over and then you have your empty bucket, and so you're down to 0. Right at the moment that it tips, that's when you have a big rain pulse, right? So all of the rain then comes out at that one moment. And then you're going to wait, you're going to have no rain while the bucket is filling up again. So it's 0, and while it's filling up, and then you have another rain pulse. So this sawtooth has to be the bucket, because it wouldn't really make sense as rain, because it doesn't gradually get rainier and rainier and rainier and then stop raining, rainier and rainier, rainier, and then stop raining. It's the bucket is filling up, filling up, filling up, and then it's back down to 0. And then the rain is just at these discrete intervals. And this is, again, what I was saying, this is how the atmosphere works, that the evaporation is more or less constant into the atmosphere, but then it comes out in chunks. Okay, so this is all before climate change. Under warming, how do these things change? So we're going to increase temperature now, let's just say 4C to get bigger numbers. Instead of 6% and 3%, let's just multiply those by 4, because that's roughly, when we look at like graphs in 2100, that's kind of the magnitude that we're looking at. So let's multiply that 3% by 4 to get 12%. So evaporation increases by 12%. So our flow going in increases. But our atmospheric capacity increases as well, and it increases more. It doubles. It's increasing by more. But that more is twice as much. And so then the rain is going to be increasing according to the capacity of the atmosphere when it rains. So the rain increases by 24% when it rains, but it's going to have to only increase overall by what goes in. So it has to increase by 12% overall. Okay, so the big challenge is to think about what these graphs will look like in a warmer climate. So first just think about how you would draw a red line on here to correspond to your new model that has been changed in this way. More flowing in and a bigger bucket, but the bucket increases more than the flow in increases. So I'd start with evaporation. Think about evaporation first. That's the easiest one. And then these ones are more difficult. So A, B, C, or D. Okay, so we've got 47% C and 28% D are our two most popular answers, and that's great. So C is correct, and D is close. D is kind of difficult to decipher from C. So let's first look at why A and B are wrong. So yeah, so in this case, we have less evaporation, less going in to the atmosphere as it warms. So that can't be right. And then, so that's the same problem with B also, right? That also showed a decrease in evaporation. And so just to follow this through the system, if you have a decrease in the amount of water going in, that means your rate of bucket filling up is less, right? So the slope of this line is less. And then what did we do to the bucket in this case? It's filling up slower, but the bucket size increased. So then when it rains, it actually does rain more because your bucket is larger. So this would be a non-physical, this doesn't actually happen in the real world, or at least in the global average anyway, situation where evaporation decreases in a warmer world, but the atmosphere can hold more water. It's hypothetically something that could be true. And if that was the case, then we would get more rain when it rains, but then a lot longer kind of time between rain events. And so then what does this, so I said that evaporation decreased in this scenario as well. And then what happened to the bucket size over here? Got smaller too. So you can tell that it's just, it fills up to a point that's below what it was before. And so when it rains less, and it's raining less frequently. I said C is correct. So we have an increase in evaporation by 12%. We have an increase in bucket size by 24%. What's wrong with D? Why is D not the right answer? In both of these, we have the increase in evaporation, so we can't really, I mean, you can kind of like pick out the numbers and think about it that way. But there's something going on with the bucket and the rain dynamics up here that make D not match the initial premise. So the bucket, you can see the bucket increases in D as well. So these both look like, what is the difference between these two? Yeah, the difference here, so in both cases, the evaporation increases. In both cases, the bucket size increases. But in D, the evaporation is increasing more than the bucket size is increasing. And so that means that because the evaporation increases more than the bucket size increases, you get an increased frequency of rain events. And so you can see that where, like, if you start counting the rain events, you're going to have more red up here than blue. They're coming more frequently. Where C is the situation that we talked about, where the bucket increases more than the evaporation increases. And so you are filling it up faster, and because the bucket increases, the bucket size increases, you get more rain when it tips. But it's that subtle attribute that the bucket size increases more than the evaporation increases. That's the key thing that causes this decrease in the frequency of rain events. More rain when it rains, but then longer time periods between the rain. If you count these, there's 19 kind of lighter rain events in the original blue, cooler climate, and then 17 heavier rain events in the warmer climate with the larger bucket and the larger evaporation. So less frequent rain, but more rain when it rains. Okay, so here's the summary in more graphical form. If we just imagine this is like an exaggerated version of this, but like we imagine this is July 1980, and here's our calendar. So this wouldn't be in California. Let's say this is in North Carolina. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9 rain clouds in our calendar. So 9 units of rain. And an exaggerated version would be in July 2050 in the same location. We have more rain. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 clouds, 12 rain clouds instead of 9. So more rain overall. But also it got clumpier. It's more rain when it rains, and then more time between those rain events. So just showing them both at the same time. This is under global warming over time, July 1980 to July 2050. More rain when it rains, more rain overall, and then more time between rain events. So here's like another visualization just showing the same thing. Instead of a calendar, just looking at a bar graph, precipitation, days. In your pre-industrial climate, it might look like this. In your 4C warmed climate, 4 degrees Celsius warmed climate, the most intense precipitation increases by 24%. And so you would see these larger events get larger, but then in order to have the total amount of precipitation be constrained by how much evaporation is going into the atmosphere from the ocean, you're going to have to eliminate some of these lower precipitation events and get more time between rain events. And so we can talk about that in terms of return periods and return values. So we did that last time with temperature, again, where we discussed these return periods were graphs where we were showing the frequency where things get less and less frequent as you go out to the right side. So a once per 1 year event, once per 10 years event, once per 100 years event, once per 1,000 year event. These are very rare. And then some value you're talking about. So temperature, this would be larger and larger values. And so in this hypothetical climate, a 1 per 10 year event was getting a temperature of 115 degrees Fahrenheit. And then in the warmed climate, that return period changed so that a 115 degree Fahrenheit value went from being a once per decade event to being a once per 1 year event. So you expect to see it every single year. And then we can also have the change in return value, which is at a given return period, if it's a once per decade event, how much does the value of that change? So in this case, it increased by 5 degrees Fahrenheit. So that's the temperature one. For precipitation, we can start out, looks basically the same, but then in the warmed climate, it looks slightly different than the temperature one, that not all of the values increase in frequency. You have a situation where at the most heavy values, like the once in 100 year events, those can become much more frequent. So in this case, I'm saying a once per 100 year event at some location has become a once per decade event. But then you have this crossover where the light precipitation events become less frequent in the warmed climate. So that's how we get to this original graph that I was showing of the more extremes. And so that's like, that tippy bucket model. That's our basic theory of how these things should work. And then you can go to advanced modeling that's going to, incorporate many more details and not going to model the atmosphere as a bucket, but actually model it based on physics. And when we do that, this is the type of thing that we get out of climate models. This is showing changes in return values of precipitation per 1 degree Celsius of warming, and then the change in return period for a present day 20-year return value. Like let's look where we are here. So we are here in our color. So this is saying that a current, or in the pre-industrial climate, if we had a return value of precipitation of, let's say, 100 units, and it's saying like how often do we expect to see that now that it's warmed 1 degree Celsius? It used to be we'd see it every 20 years, but now we expect to see it every 13, 14 years. So that has increased in frequency. And then this is saying the return value, the actual value here, how much has this changed for a 20-year return value? And so that's saying that's increased by, for us, something close to like 5%. And then looking at the end of the century, future return period for present day 20-year return values for the wettest day. So this is saying in 2100 under high emissions, if we're here, we're in this about 5 is the value here. So this is saying what used to occur every 20 years on average would occur every 5 years on average. That's that rain part. And then there's the period between rain events. And so this is usually measured by something called consecutive dry days, which is just measuring the number of days between rain events. And so we see this is actually like the map here is much more kind of muddled. You have different predictions in different locations. And so these blue areas are showing where we actually do expect to see a decrease in consecutive dry days. And so this is less straightforward, and that's where the tippy bucket model doesn't apply to all locations. But some locations like Brazil, the Amazon, for example, that would be a location where this tipping bucket model applies well, because we're expecting to see large increases in the frequency of very heavy precipitation events and large increases in the time between precipitation events. And so when we look, these are modeling exercises kind of hitting the system with very large greenhouse gas increases. And so you can kind of see the signal emerge pretty well. But when we look at actual observations historically, we expect this to be kind of buried in the noise of just natural variability. There's just huge variability from year to year, day to day, just naturally. And so far that, 1 degree Celsius rise in temperature, we think, is imposing that basic change that we've been discussing today underneath all of that variability. But it's still very hard to actually see in the historical record because it's kind of buried in that variability. It's like searching for a needle in a haystack historically. But we do kind of see the signal emerging now in terms of the most extreme precipitation events in some locations. So this is a map of the trend in these most extreme one-day precipitation events. And so this is the zero line. So anything on the left side is going to be a decrease, and anything on the right side is going to be an increase. And so if we just look, for example, over the eastern United States, this is what that looks like through time, as we see kind of a slight increase in the most extreme one-day precipitation events. But then if we look at these consecutive dry days, this is the same idea. Is it increasing or decreasing consecutive dry days historically? So not just what the models say, not what the theory says, what do observations say? It's pretty muddled. We don't really see like a strong, consistent global pattern. Some locations where models project that this should be happening isn't necessarily happening, like in Australia. And then if you look at any given location, this is like looking in Mexico, not a super strong signal. So this is the type of thing that you're just not sure. You're not sure if the model's wrong. You're not sure if it's just the signal to noise ratio is too low. You're not sure when and if that will emerge, or if our understanding will be altered in the future. And so that's the state of the science in a lot of these extreme events, is that there's not nearly the consensus around these types of things as there is around global average temperature and these other kind of broad scale measurements of climate change.